temperature, it is called standard enthalpy. For example, the standard state of liquid ethanol is pure liquid ethanol at 298 Kelvin and 1 bar pressure, and the standard state of solid iron is pure iron at 500 Kelvin and 1 bar pressure. Let us now look at the enthalpy changes during phase transformations. We know that the intermolecular forces in the three states of matter are different. Therefore, the amount of energy required to convert matter from one state to another also differs. Standard enthalpy is represented as delta H naught, where the superscript naught indicates the standard state. The process by which matter is converted from one state into another is known as phase change or phase transition. The enthalpy or heat changes accompanying these phase changes are enthalpy of fusion, enthalpy of vaporization, and enthalpy of sublimation. Let's look at each type in detail. Standard enthalpy of fusion is the enthalpy change accompanying the melting of 1 mole of a solid substance in standard state into its liquid state. It is also called as molar enthalpy of fusion and is represented as delta fusion H naught. For example, the amount of heat required to melt 1 mole of ice at 273 Kelvin is 6 kilojoules. Thus, we can say that the molar enthalpy of fusion of ice is plus 6 kilojoules per mole. As the melting of a solid is an endothermic process, all enthalpies of fusion are positive. We know that freezing is the reverse of fusion. Thus, the enthalpy of freezing, also known as enthalpy of solidification, is the same as enthalpy of fusion, except that it has the opposite sign, that is, a negative sign. Now let's look at the enthalpy of vaporization. The amount of heat required to convert 1 mole of a liquid into its vapor state at constant temperature and under standard pressure is called its standard enthalpy of vaporization or molar enthalpy of vaporization. For example, the amount of heat required to convert 1 mole of water into vapor at temperature 373 Kelvin is 40.79 kilojoules. Thus, the molar enthalpy of vaporization of water is plus 40.7 kilojoules per mole. We know that condensation is the opposite of vaporization. Thus, the enthalpy of condensation has the same value as the enthalpy of vaporization, except that it has the opposite sign, that is, the negative sign. Now, let's look at the enthalpy of sublimation. Sublimation is a process in which a solid changes directly into vapor state without any intermediate liquid state. Enthalpy of sublimation is defined as the enthalpy change accompanying the conversion of 1 mole of a solid directly into vapor phase at constant temperature and under standard pressure. For example, the amount of heat required to sublime 1 mole of iodine is 62.4 kilojoules. Thus, we can say that the molar enthalpy of sublimation of iodine is plus 62.4 kilojoule per mole. The magnitude of the enthalpy change in phase transformations depends on the strength of the intermolecular interactions between the molecules in the substance undergoing phase change. For example, it requires about 40.79 kilojoules of energy to vaporize 1 mole of water, while it requires only 29 kilojoules of energy to vaporize 1 mole of acetone. This can be explained in accordance to the fact that the water molecules are held together in the liquid state through hydrogen bonding, while the acetone molecules are held together only through weaker dipole-dipole interactions. Thus, it requires less heat to vaporize 1 mole of acetone than 1 mole of water. The enthalpy change associated with the formation of 1 mole of a compound from its constituent elements, all substances being in their standard states, that is, at 298 Kelvin and 1 bar pressure, is called the standard molar enthalpy of formation. It is represented as delta FH naught. The subscript F indicates that 1 mole of compound has been formed in its standard state from its elements in their most stable states. For example, when carbon and oxygen in their elemental states react to form 1 mole of carbon dioxide, 393.5 kilojoules of heat is produced. Hence, we can say that the standard enthalpy formation of gaseous carbon dioxide is minus 393.5 kilojoules per mole. However, the reaction of formation of water from its elements does not represent the standard enthalpy of formation of water. This is because the heat, 571.6 kilojoules per mole, is evolved when 2 moles of water are formed from the elements at the standard state. This can be referred as enthalpy of reaction. The standard enthalpy of formation in this case would be minus 571.6 divided by 2, that is, minus 285.8 kilojoules per mole. By convention, the standard enthalpy of formation of all elements is assumed to be 0. We can calculate the heat of reaction under standard conditions from the values of standard heat of formation of various reactants and products. The standard enthalpy of reaction can be calculated as the sum of standard enthalpies of formation of products minus the sum of standard enthalpies of formation of reactants. Let's see how we can apply this formula. Let's say that we have to determine the amount of heat required to decompose calcium carbonate to lime and carbon dioxide, given that all the substances are in their standard state. We can use the formula of standard enthalpy of reaction to determine the enthalpy change of the reaction. Thus, we get enthalpy of reaction equals enthalpy of formation of products, that is, lime and carbon dioxide, minus enthalpy of formation of the reactant, that is calcium carbonate. On substituting the values of standard molar enthalpy of formation of the reactants and products from the table of standard molar enthalpy of formation of substances, we get the amount of heat as plus 178.3 kilojoules per mole. Thus, the plus value of the standard enthalpy of reaction indicates that the decomposition of calcium carbonate is an endothermic reaction. Note that the stoichiometric coefficients for all the compounds in the given equation are 1. Now, let us look into the thermochemical equations. Hess's law states that if a chemical change can be made to take place in 2 or more different ways, whether in one step or more than one step, the amount of total heat change is the same no matter by which method the change is brought about. For example, the enthalpy of an overall reaction A gives rise to B along one route is delta RH. Now, if the same reaction occurs through another route, delta RH1, delta RH2, delta RH3, then we can say that delta RH equals the sum of delta RH1, delta RH2 and delta RH3. Let's understand this through a chemical reaction. When sulfur in its elemental state burns to form sulfur trioxide in one step, the heat evolved during the chemical equation is minus 395.4 kilojoules per mole. Now, let's break down the reaction into two steps. In the first step, sulfur reacts with oxygen to form sulfur dioxide. The heat evolved during the chemical equation is minus 297.5 kilojoules per mole. In the second step, sulfur dioxide reacts with oxygen to form sulfur trioxide. The heat evolved during the chemical equation is minus 97.9 kilojoules per mole. If we add the heat evolved from both steps, we get minus 395.4 kilojoules per mole. Note that the amount of heat evolved through the two steps is the same as the amount of heat evolved in one step, thus proving Hess's law. Combustion is a process of burning a chemical compound at high temperatures in presence of excess of oxygen or air. Combustion reactions are exothermic reactions. The energy released during these reactions is used to drive automobiles, ships, airplanes and trains, to operate industrial processes, rocketry, and for numerous other purposes. The energy change accompanying the process of combustion is called the enthalpy of combustion. It is defined as the amount of heat energy evolved when 1 mole of substance is completely burnt or oxidized in excess of air or oxygen, and is represented as delta CH. For example, when 1 mole of carbon is completely burnt, it releases 393.5 kilojoules of heat. The negative sign of enthalpy change indicates the exothermic nature of the reaction. The enthalpy of combustion is considered only if the substance oxidizes completely. For example, if carbon is oxidized to form carbon monoxide, then the heat of the reaction is minus 110.5 kilojoules per mole. Since carbon does not oxidize completely, the heat evolved during the reaction is not considered as the enthalpy of combustion. Standard enthalpy of combustion is defined as the enthalpy change per mole of a substance when it undergoes combustion, with all the reactants and products being in their standard states at the specified temperature. It is represented by delta CH0. Combustion reactions release large amounts of energy. For example, 1 mole of butane on complete combustion produces minus 2658 kilojoules per mole of energy. The energy released by the combustion of food or fuel is usually compared in terms of their combustion energy per gram, which is known as calorific value. Calorific value of food or fuel is defined as the amount of heat released by the complete combustion of 1 gram of fuel or food. Calorific value is usually expressed in kilojoules per gram or kilocalorie per gram. When 1 mole of glucose burns, it releases 2820 kilojoules of heat. Hence, The calorific value of glucose is 2820 divided by 180, which is equal to 15.67 kilojoules per gram. Now let's look at enthalpy of atomization. When 1 mole of a given substance dissociates into gaseous atoms, the enthalpy change accompanying the process is called the standard enthalpy of atomization. It is represented by delta AH0. Let's consider the atomization of dihydrogen into hydrogen atoms. In this reaction, hydrogen atoms are formed by breaking of HH bonds in dihydrogen. The conversion of 1 mole of hydrogen molecules into hydrogen atoms requires 435.5 kilojoules per mole of energy. Therefore, the enthalpy of atomization of dihydrogen is 435.5 kilojoules per mole. Now let's look at bond enthalpy. We know that chemical reactions involve the breaking and making of bonds. The breaking of bonds requires energy, while the making of bonds involves the release of energy. The enthalpy changes associated with chemical bonds are expressed in terms of bond dissociation enthalpy and mean bond enthalpy. Let us try to understand these terms with reference to diatomic and polyatomic molecules. In case of diatomic molecules, bond dissociation enthalpy is the change in enthalpy when 1 mole of covalent bonds of a gaseous covalent compound is broken to form products in the gas phase. For example, a 435.5 kilojoule per mole of energy is required to dissociate 1 mole of hydrogen gas into hydrogen atoms. Hence, the bond dissociation enthalpy of hydrogen is 435.5 kilojoules per mole. Note that this is the same as the enthalpy of atomization of hydrogen gas. For all diatomic molecules, bond dissociation enthalpy is the same as atomization enthalpy. In case of polyatomic molecules, bond dissociation enthalpy is different for different bonds within the same molecule. For example, the enthalpy of atomization of methane is 1665 kilojoules per mole. Although the 4 CH bonds are identical in terms of bond length and energy, the energy required to break individual CH bonds in each successive step is not the same. The energies required to break these bonds are successively plus 427, plus 439, plus 452, and plus 347 kilojoules per mole, respectively. The total energy required is plus 1665 kilojoules per mole. Hence, in such cases, we use the term mean bond enthalpy instead of bond dissociation enthalpy. Thus, mean CH bond enthalpy in methane is 416 kilojoules per mole. Bond enthalpies can be calculated using Hesss law. The knowledge of bond enthalpies helps us in predicting the enthalpy of a reaction in gas phase. The standard enthalpy of a reaction, delta RH0, is equal to sigma bond enthalpies of reactants minus sigma bond enthalpies of products. It is important to remember that this relationship is approximate and valid only when all the reactants and products in the reaction are in gaseous state. We have learned that if a process is carried out at constant volume, then the heat content is the same as the internal energy as no work is done. but most of the chemical reactions are carried out at constant pressure and not at constant volume. When a reaction is performed under constant pressure, then it may involve change in the volume. The energy change occurred during such reactions may not only involve change in internal energy but also do some work. To understand this, assume a chemical reaction occurring at a constant pressure. Let us assume that the reaction is exothermic and also involves gaseous substances. When the reaction proceeds at constant pressure, two possibilities arise. One possibility is that if the reaction is carried out with increase in volume, then the system has to expand against atmospheric pressure and energy is required to perform this act. As some of the energy has to be utilized for this purpose, the heat evolved in this case would be a little less than the heat evolved at constant volume conditions. The other possibility is that if the reaction is carried out with decrease in volume at constant pressure, then the work is done on the system and heat evolved would be greater than the heat evolved at constant volume. Thus, it can be concluded that heat changes occurring at constant pressure and temperature are not only due to change in internal energy but also due to expansion or contraction against the atmospheric pressure. Hence, the scientists felt the need to study the heat changes at constant pressure and temperature. In order to study the heat changes in a chemical reaction at constant temperature and constant pressure, a new thermodynamic function called enthalpy was introduced. The total heat content of a system at constant pressure is equal to the sum of the internal energy and PV. This is called the enthalpy of a system, which is represented by H. Note that enthalpy is also called as heat content. Enthalpy, which depends on the three state functions, internal energy, pressure, and volume, is also a state function. Every substance has a definite value of enthalpy. Like internal energy, enthalpy of a substance cannot be measured. However, it is possible to measure the change in enthalpy. The change in enthalpy is equal to the difference between enthalpy of products and enthalpy of reactants. The change in enthalpy may be expressed as delta H is equal to enthalpy of products, HP, minus enthalpy of reactants, HR. The significance of delta H also follows from the first law of thermodynamics, as delta U is equal to QP minus P delta V. Here, QP represents the heat absorbed by the system and minus P delta V represents the work done by the system. Let U1, U2, V1 and V2 represent the initial and final internal energies and volumes respectively. The above equation can be written as U2 minus U1 equal to QP minus P into V2 minus V1. On rearranging this, we get QP equal to U2 plus PV2 minus U1 plus PV1. But we've already learned that U plus PV equal to enthalpy H. Hence, the equation can be written as QP equal to H2 minus H1 is equal to delta H. Therefore, delta H is equal to QP. For finite changes at constant pressure, we can write the equation as delta H is equal to delta U plus delta PV. Since P is constant, we can write as delta H is equal to delta U plus P delta V. Remember that delta H is equal to Qp, the heat absorbed by the system at constant pressure. Delta H is negative for exothermic reactions and positive for endothermic reactions. Let's now look at the relation between delta H and delta U. When we deal with solids and liquids, the difference between the change in internal energy, delta U, and enthalpy, delta H, is not significant. This is because solids and liquids do not show significant change in the volume when heated. Thus, if change in volume, delta V, is insignificant, it implies that change in enthalpy, delta H, equals change in internal energy, delta U. The difference between the change in internal energy and enthalpy becomes significant when gases are involved in the reaction. Let's consider a chemical reaction occurring at constant temperature, T, and constant pressure, P. Now, let's say that the volume of the reactants is VA and the number of moles in the reactants is Na. Similarly, the volume of the products is VB and the number of moles in the product is Nb. We know that according to the ideal gas equation, PV equals nRT. Thus, for the reactants, PVA equals NART, and for the products, PVB equals NBRT. Thus, PVB minus PVA equals NBRT minus NART, or PVB minus VA is equal to NBRT minus NART, or PVB minus VA equal to NB minus NART. That is, pressure P multiplied by change in volume, delta V equals change in number of moles of gas, delta N GRT. Note that delta N is the number of moles of gaseous products minus number of moles of gaseous reactants. We learned that change in enthalpy delta H equals change in internal energy delta U plus product of pressure P and change in volume delta V. On substituting the values, we get change in enthalpy delta H equals change in internal energy delta U plus change in number of moles of gas delta N GRT. This relation helps us in calculating the change in enthalpy from change in internal energy and vice versa. Now let's learn about heat capacity. The capacity to absorb heat energy and store it is known as the heat capacity of a system. The heat absorbed by the system appears as rise in temperature. The increase in temperature is proportional to the heat transferred, which can be written as Q equals coefficient multiplied by change in temperature delta T. Note that the value of the coefficient depends on the size, composition, and nature of the system. The equation can also be written as Q equals C multiplied by delta T, where C is called the heat capacity of the system. If Q calories is the heat absorbed by the system and the temperature rises from T1 to T2, the heat capacity C is given by the expression C equal to Q by T2 minus T1. Thus, heat capacity is defined as the amount of heat required to raise the temperature of the system by 1 degree at a specified temperature. The specific heat capacity is the quantity of heat required to raise the temperature of unit of mass of a substance by 1 degree Celsius or by 1 Kelvin. Thus, the expression for Q in terms of specific heat capacity becomes Q equals specific heat capacity C multiplied by the mass m multiplied by change in temperature delta T. The molar heat capacity of a substance is defined as the quantity of heat needed to raise the temperature of 1 mole of substance through 1 degree Celsius or 1 Kelvin. The SI unit of molar heat capacity is joule per degree Kelvin per mole. The molar heat capacity Cm equals heat capacity C divided by N, where N is the amount of the substance. Heat is not a state function, neither is heat capacity. Hence, it is necessary to specify the process by which the temperature is raised by 1 degree. The two important types of molar capacities are molar heat capacity at constant volume and molar heat capacity at constant pressure. Let us see the relation between molar heat capacity at constant volume, which is denoted by Cv, and molar heat capacity at constant pressure, which is denoted by Cp. We learnt that the equation for heat Q is the product of heat capacity and change in temperature delta T. Therefore, at constant volume, heat Qv equals product of heat capacity at constant volume Cv and change in temperature delta T. But the heat absorbed at constant volume is equal to change in internal energy. Thus, Cv into delta T can be written as equal to delta U. Similarly, at constant pressure, heat Qp equals product of heat capacity at constant pressure Cp and change in temperature delta T. We have seen that at constant pressure the heat absorbed by the system is equal to the change in enthalpy. Hence, Cp into delta T can be written as equal to delta H. The difference between Cp and Cv for 1 mole of an ideal gas can be derived as follows. The change in enthalpy for 1 mole of an ideal gas can be written as delta H equals delta U plus delta Pv. For 1 mole of an ideal gas, Pv is equal to RT. Hence, the equation can be written as delta H equals delta U plus delta RT. As R is constant, the equation can also be written as delta H equal to delta U plus R delta T. On substituting the values of delta H and delta U in the equation, we get Cp multiplied by delta T equals Cv multiplied by delta T plus R delta T. Since delta T is equal to 1, we can write the equation as Cp equal to Cv plus R, or Cp minus Cv is equal to R. Before we begin, let's look at this cold pack. Instant cold packs are often used by athletes for treating bumps and bruises. We know that a cold pack is not pre-cooled. Then, how does it become cold without being refrigerated? A cold pack contains 2 pouches, one filled with water and the other filled with a chemical substance. When the pack is squeezed, the pouches break and the chemical substance dissolves in water. The chemical reaction in the pouch absorbs heat energy from the surrounding. The temperature of the surrounding decreases, causing the pouch to become cold. The amount of heat energy released or absorbed when 1 mole of a substance dissolves in a specified amount of solvent is known as enthalpy of solution. For example, the ions of an ionic compound, AB, are held together by electrostatic forces of attraction. When it is dissolved in a solvent, its ions leave their ordered positions on the crystal lattice. Certain amount of energy is required for conversion of an ionic compound to its ions. This energy is known as lattice enthalpy and is denoted by delta lattice H0. Slowly these ions start moving freely in the solution and start interacting with the solvent particles. When water is used as a solvent, the dissolving process is called as hydration. If any other solvent is used, then the process is known as solvation of ions. Energy change occurs in dissolving of AB ions in the solvent is known as enthalpy of hydration of ions and is represented as delta hydration H0. As dissolution proceeds, the ions leave their lattice site and get mixed with the solvent. This total energy change of the solution is known as enthalpy of solution and is represented by delta solution H0. Thus, we can conclude that the enthalpy of solution of ionic compound AB is the sum of change in lattice enthalpy and enthalpy of hydration of ions. Let's look at the terms hydration enthalpy and lattice enthalpy. Enthalpy of hydration, delta hydration H0 of an ion is the amount of energy released when a mole of the ion dissolves in a large amount of water, forming an infinite dilute solution in the process. Lattice enthalpy, delta lattice H0 of an ionic compound is the enthalpy change which occurs when 1 mole of an ionic compound dissociates into its ions in gaseous state. The lattice enthalpy of a compound depends on the size of its ions and the charge on them. A decrease in the size of an ion increases the lattice enthalpy. That is, the enthalpy becomes negative and the reaction becomes exothermic. This happens because small ions tend to be closer to each other and have a shorter distance of separation, which results in a larger attraction force between the ions. Thus, lattice energy increases, that is, it becomes more negative. Alternatively, an increase in charge also increases the lattice enthalpy. That is, it becomes more negative. This is because the attraction forces between ions increases as the charge increases. It is not possible to determine lattice enthalpy through an experiment. But the same can be calculated by constructing an enthalpy diagram known as von Haber cycle. Let's look at an example. We know that the enthalpy change involved in the formation of a compound is called the enthalpy of formation. In this example, the enthalpy formation of sodium chloride from sodium in solid state and chlorine in gaseous state is minus 411 kilojoules per mole. Now, let's illustrate the different steps involved in the formation of sodium chloride. First, solid sodium changes to gaseous sodium atoms. The enthalpy change involved in this step is known as enthalpy of sublimation, and its value is plus 108.4 kilojoules per mole. In the next step, gaseous sodium atoms are ionized to form sodium plus 1 ions. The enthalpy change involved in this step is called ionization enthalpy, and its value is plus 496 kilojoules per mole. Similarly, the dissociation of chlorine takes place, and the enthalpy of dissociation is plus 121 kilojoules per mole. This is followed by chlorine atoms changing into chloride ions. Chlorine gains an electron, and the electron gain enthalpy is minus 348.6 kilojoules per mole. Finally, the gaseous ions combine to form solid sodium chloride. The enthalpy change involved at this step is known as lattice enthalpy. Let's apply Hess' law to determine the lattice enthalpy released in this step. Hess' law states that the enthalpy of change in a particular reaction is the same whether the reaction takes place in one step or in number of steps. Thus, enthalpy of formation equals enthalpy of sublimation of sodium plus enthalpy of dissociation of chlorine plus enthalpy of ionization of sodium plus electron gain enthalpy of chlorine plus lattice enthalpy. On substituting the values of all the enthalpies, we get the value of lattice enthalpy as minus 788 kilojoules per mole.